Okay, so we left off here. You equate the two energy components, or the two first components of the form momentum, uh, before the collision, before the decay, and after the decay. E over c is just gamma mc, right? So that's what always goes in this position, and and uh, and so gamma is basically associated with the velocity of the ejecta. Okay, the velocities of the ejecta. So we can plug this in here. Okay, we can plug this in there, and eventually, quickly, we just get to gamma is equal to m over 2m. Okay, so it's the ratio of the mass that you start with before the decay to the sum of the masses that you have afterwards. Okay, remember, this is where we've basically assumed where m1 is equal to m2 equals m. Okay, so now once you have gamma, right, then we know that gamma squared is equal to 1 over 1 minus beta squared, and so eventually you get that beta squared is equal to 1 minus 1 over gamma squared, which is equal to 1 minus 4 little m squared over big M squared. Okay, so this, of course, gives us the velocities of the ejecta, and so for this simple case where the two masses are the same, then you can get to that pretty quickly and pretty easily. Now, this again is sort of as I said when I introduced this decay problem. This is basically similar to what happens in fission, and so this will allow you in principle to calculate the energies and the kinetic energies and the velocities of the ejecta, which is generally what you're looking for in these kinds of problems. Okay, so that concludes the lecture for today. Next week we'll talk about Compton scattering, which involves photons, and we will then start our transition into our quantum mechanics portion of the course.